Let's look at some more examples of the fundamental theorem of calculus part 2. A couple of things I'd like to point out in this statement of the fundamental theorem of calculus part 2 is, first of all, notice that the lower bound has got to be a constant. Also, if you're going to apply FTC2 in a straightforward way, notice that the variable in big F has got to be an exact match for the upper bound. This has got to be a plain old x. So you can't have an x squared, you can't have sine x. This has just got to be a constant on the bottom, and it's got to be an x on the top. If you want to apply the fundamental theorem of calculus, if these two things don't hold, then you need to make a couple of adjustments. So let me give you some examples where I show you the adjustments that you can make. Look at this problem. Suppose that big F of x were equal to the integral from x to 5 of 1 over t squared. Notice here that it's not exactly of this form. Notice that the constant is at the top instead of at the bottom. So before we apply the fundamental theorem of calculus, we need to apply one of the properties of integrals, definite integrals, which says that you can swap the two bounds, here putting the 5 on the bottom and the x on the top, provided you change the sign of the integral. So the first step is going to be to swap the bounds so the constant's on the bottom and the x is on the top, and then we can calculate the derivative. So for the derivative, I'll bring down the minus sign, and I'll replace the t here with x. So I get negative 1 over x squared. One thing I want to make sure that you see is that this is two separate sentences. This first line represents the function big F. This sentence here represents the derivative of big F. So please don't make the mistake saying that this integral is equal to this. That's not true. The derivative of this integral is equal to negative 1 over x squared. Now here's another one, which is an even bigger problem. Suppose that big F of x is equal to the integral from 3 to x squared plus 2x times the square root of the square root of t dt. So the problem here is that even though the lower bound is a constant, as is required, the upper bound is not plain old x. In this situation, you must use the chain rule. Now what makes this feel weird is that the inside function is the function up here. This isn't considered the inside. This is the inside. This is where we expect that x to be. So let me maybe restate the fundamental theorem of calculus using in the form of the chain rule, and then let's do this problem. So let's clear some space. Here's the chain rule version. Of the fundamental theorem of calculus part 2. If big F of x is equal to the integral from a constant to a function of x of little f of t dt, then big F prime of x is going to be gotten by taking the u and substituting it into the t. So that'll be f of u of x, but then you multiply by the derivative of the inside, where this is considered the inside. So the derivative is obtained by taking the expression up here, substituting it in for x, but then you multiply by the derivative of whatever is up here. So let's apply the chain rule to this problem. F prime of x is going to be the square root of x squared plus 2x multiplied by the derivative of x squared plus 2x, which is 2x plus 2. So you take whatever's up in here, you substitute that in for t, and then you multiply by the derivative of what's up there, the derivative of the upper bound. Let's practice that again. Let's say that the big f of x is equal to the integral from 2 to x to the fourth of t squared plus 3t. Then to take the derivative, first of all, you replace each t with x to the fourth. So it'll be x to the fourth squared plus 3x to the fourth. And then you multiply by the derivative of what's up here, the derivative of the upper bound. So that will give me x to the 8th plus 3x to the 4th multiplied by 4x cubed. Now there's one other situation I need to show you. And let me maybe save that for, no, I think I can still do it in this video. Let's continue. Here's one more example. And this is as bad as it's going to get on the test. And that'll be a problem like this. F of x is equal to the integral from x squared to x cubed t over t squared plus 1. So I think you can see what the problem is. Notice that not only is the lower bound not a constant, but both of them are expressions different from plain old x. So here's the trick on this. This is not really what the graph looks like, but let's just pretend that the graph of this function, little f of t, looks something like this. And we're integrating from x squared to x cubed. So the integral goes from here to here. The cumulative area function represents this area in between. What we're going to do is we're just going to pick some number. I'm going to choose 1, but the particular number is not important. And recognize that the integral from x squared to x cubed is going to be the same as the integral from 1 to x cubed minus the integral from 1 to x squared. So the area between here and here is equal to the total area minus the area on the left. Writing that in symbols, the integral from x squared to x cubed is equal to the integral from 1 to x cubed minus the integral from 1 to x squared. So just look at what this is saying. The area between here and here equals the big area minus the left-hand area. So now let's fill in the integrand. T over t squared plus 1, t over t squared plus 1. So now we've taken care of one of the problems, which is that the lower bound was not a constant. Now we have two integrals, and each of those does have a constant as the lower bound. Now, I'm going to put a period, starting a new sentence. Here's f prime. To find the derivative, I take this upper bound and plug it in for all the t's, and then I multiply by the derivative of the upper bound. So first of all, with the x cubed, I'm going to plug it in for each t. So I'll have x cubed over x to the 6th plus 1, and then I multiply by the derivative of the upper bound, which is 3x squared, minus, and now I do it for the second integral. I replace each of the t's with an x squared, so that's x squared over x to the 4th plus 1, and then I multiply by the derivative of the inside, which is 2x. So simplifying just a little bit, I'll multiply the 3x squared into the numerator to get 3x to the 5th over x to the 6th plus 1 minus 2x cubed over x to the 4th plus 1. And that's my derivative.